Thank you, Larissa, for that very gracious introduction. Thank you to the CEDAR Science Steering Committee for choosing me to give this presentation. And thank you all for showing up first thing in the morning. So as promised, I'm going to be talking about the role of tides and planetary waves in atmospheric vertical coupling. And I'm going to focus on observation-oriented results, in particular from the last 10 years. And now I'm going to focus on seeing if I can advance the screen. Great. So we all know that during the quiet time, the ionosphere is still varying very substantially above background levels, due presumably to influences from the lower atmosphere, such as tides, planetary waves, gravity waves, extreme events like sudden warming, and impulsive events like explosions, volcanoes, tsunamis. So I always like to show this as Exhibit A. It's, no, I intend no pun here, but it has truly become an iconic figure of our time. And it was first published by Thomas Simmel in 2006, and it shows a wave number 4, a sort of a four-crested, oops, sorry, got mixed up between the pointer and the advancer. So it shows a kind of a wave number 4 pattern embedded in the equatorial ionization anomaly. This is a phenomenon that emanates from about 350 kilometers. And this pattern was linked numerically to a four-peaked diurnal tide that originates in the tropical, in the kind of tropical large-scale convection. A second great example I love to show is this figure from a paper by Koki Chow in 2009, showing the evolution of vertical drift during the daytime at Hikamarka. And it tells us that during the days surrounding a sudden warming in January 2008, it's all these colored curves, the drift patterns differed radically than their usual climatological patterning, which is the black curve in its, in its 1 sigma outliers. Seem to have lost the pointer. Okay. So what I'm hoping to leave you with at the end of this presentation is some appreciation for how do tides and planetary waves couple the atmosphere vertically, and how does the coupling, as it's engendered within neutral atmosphere parameters, how does this imprint upon the F region? How are recent missions helping us to meet the goals from the decadal survey of understanding atmosphere-ionosphere coupling, and what challenges remain? So I thought that I would just kind of go very briefly through an explanation of what diurnal tides and planetary waves are. In the atmosphere, tides are mostly thermally forced, meaning they're forced from heating, in this case the sun, as opposed to the gravitational tides that raise the ocean surface. And in the atmosphere, the sun, the sun heats the atmosphere through ozone, as we all know about, but also through water vapor at Earth's surface, which is actually a very powerful forcing. It's very strong, and it kind of picks, water vapor picks up a lot of tropospheric patterns, a lot of weather patterns, and longer-term variation patterns. And because the sunlight is active only during the day, it's either zero or it's positive, and this decomposes into a diurnal cycle, a semidiurnal cycle, a 24-hour period, a 12-hour period, and even higher subharmonics. The tides are governed by the usual Navier-Stokes lineup here. In terms of momentum, they are controlled by pressure gradient. This out. Let's go back here. They are controlled by pressure gradient forces, Coriolis forces, tendencies due to the forcing, conservation of mass, that's the continuity equation there, first law of thermodynamics. And I thought I would just show a slide or two to demonstrate what tides look like. And I'm going to focus right now on their behavior in the tropics, where there's a very weak or zero Coriolis force. And what you're seeing here is really a typical gravity wave kind of dynamics. Global scale, the tides are global scale, and this is a wave number 2 pattern. It is a semidiurnal tide migrating westward. And at the tropics, the wind patterns, the vectors here, are controlled by pressure gradient forces. So here the pressure gradient force is directed from high to low pressure. So at this particular point, the parcel will be accelerated eastward. And that's in fact exactly the wind pattern that appears a 1/4 cycle upstream. At higher latitudes, the Coriolis force starts kicking in. And so we transition from this purely divergent wind pattern. I should have pointed out here that where we have that as a result of the pressure gradient, there are regions of divergence and convergence of air, which has to be balanced through mass conservation by vertical motion, rushing in to either fill up or evacuate the vertical column. This is how the tidal effects are transmitted or propagated vertically through the divergence. And as we move up to higher latitudes, the Coriolis force kicks in, which pulls air parcels to the right in the northern hemisphere. And so at this point in the wave, at about 50 degrees or so, you'll see that the response of the wind is primarily to the Coriolis force, which will drag it to the right in the next quarter cycle. And that's what appears 1/4 cycle upstream. This is a solution of the semidiurnal tide. It's clean looking, easy to interpret, I think. And I'm showing now the result for the diurnal tide, the 24-hour tide, which, despite looking quite different, is governed by the exact same set of dynamics. Pressure gradient forces at the equator, which in this case are operating more in the north-south direction. Divergence and convergence, vertical motions. And then that inertial effect, that's the Coriolis effect. The inertial effect is starting to kick in much closer to the equator, like at around 30 degrees. And that accounts in part for some of the extra level of complexity in the meridional dimension for the diurnal tide. But it's the exact same dynamics. So I mentioned vertical propagation. So this is a plot showing latitude and altitude. Sorry, I scaled the altitude. So the range here is roughly 30 to 90 kilometers. And so this is the diurnal tide vertical structure. It propagates poleward of 30 or 40 degrees, equatorward of 30 or 40 degrees, amplifies vertically. This particular model I used to generate the plot only goes up to 100 kilometers, but some diurnal tides continue propagating above 100. And this is the semidiurnal tide, which propagates everywhere, so I only plot here the amplitude. And a couple of things to note is that at high latitudes, the semidiurnal tide is more significant than the diurnal tide. And that's, I guess, what I'm going to mention at this point. Now, I talked about tides, which had very fixed tendencies at 24 or 12 hours. And I'm now going to kind of pivot to planetary waves, which are much slower features, at least compared to tides. And I'm going to be introducing the topic by talking about quasi-stationary mid-latitude planetary waves of the variety that are mostly seen in the wintertime. And these are forced by, big surprise, quasi-stationary surface features, like topography, or more commonly, the differential heating properties of the continents and the oceans, especially in the northern hemisphere. So these set up big, nearly stationary waves. And that being the case, there's a strong temptation to just kill off the tendency term and look and see what we get in a purely stationary case. So if we do that, note several things here. Going to the thermodynamic energy equation, there's no evolution of internal energy here. If we're far away from the region of forcing or heating, like the surface, If we're far away from the surface, like the troposphere, stratosphere, even the mid-troposphere, then Q disappears, the diabatic heating disappears. And so that means that there's no work done in a stationary wave. And in the atmosphere, most work is done through vertical motion, through the atmosphere working on or being worked on by the stable stratification. So there's no vertical motion in a stationary wave. Therefore, there is no divergence in a stationary wave. And we get a very clean, closed-form solution here, where the winds are proportional to the pressure gradients. And the solution is flow parallel to the pressure surfaces. And as every meteorologist learns very quickly in Meteorology 101, the air flowing parallel to the pressure surfaces has low pressure on the left in the northern hemisphere. And an excellent example of this is the steady-state polar vortex, where the winds are basically spinning in a circumpolar pattern around the North Pole from west to east, technically cyclonically. So I bring up these stationary waves for one reason to illustrate how easy it is to visualize what's going on when you're dealing with a nearly stationary situation. All you need to do is look at the pressure surfaces, look at the contours of pressure, which is a meteorological observable. It's like ground zero in meteorological observations. They come from radiosondes, they can be derived from operational satellites. All you have to do is look at the pressure surfaces on a weather map, and right away you will know or get a very good idea which way the wind is blowing. So one virtue of these so-called balanced winds is that they are readily calculated and visualized from observed pressure. So as tempting as it was to get rid of those tendency terms, we really can't, because basically if there was no tendency, there'd be no weather, there wouldn't be a very interesting atmosphere. So we have to put them back, which makes this system look a bit more daunting. But one way to cope with it is to, I know this sounds counterintuitive, but is to define a new variable, this funky variable called vorticity, which is the curl of the horizontal wind, dv dx du dy. And if you assume that the winds are very close to being static, then that vorticity turns out to be proportional to the Laplacian of the pressure field. And this whole messy system collapses down into a fairly, as meteorology, as atmospheric science goes, a fairly simple expression governing the tendency of the pressure. So now let's look at a more realistic situation, a so-called quasi-stationary wave right here. Now we've got a wave going on. Where's the pointer? Okay, now we've got a wave going on. Remember, since the winds are nearly geostrophic, we can visualize the winds, which are flowing parallel to the pressure gradient. And so now we not only are able to visualize the winds, but we are, thanks to this collapsed equation here, we're able to visualize the evolution of this wave because we have an equation telling us how the second derivative of the pressure, Laplacian of the pressure, which everyone remembers from Calculus 101 is just the negative of the wave that we started out, proportional to the negative wave that we started out with, scaled by the wave number. So now we can learn that the evolution of this wave is going to be to the west, because to the west of the crest of this wave, in meteorological parlance, it's known as a ridge. To the left of the ridge is positive transport of Coriolis gradient, which is positive all over the globe. The Coriolis force is proportional to sine phi, sine of latitude. So the tendency of the Laplacian is negative to the left of the ridge, positive to the right of the ridge, which means that this whole wave is going to propagate slowly to the west. This was probably history's first true weather forecasting equation, and it was derived in 1939 by Carl Gustav Rossby. And so again, the virtue of quasi-stationary planetary waves, in fact, the virtue of planetary waves practically at any period, larger than 2 days or so, is how easy it is to visualize them in the pressure surfaces, and not only that, but how easy it is to even predict how they are going to behave. So these waves move very, very slowly westward relative to the background wind. So I just want to mention a few more little important factoids about quasi-geostrophic waves. These waves do propagate upward to a degree. They can propagate only in rather special circumstances, which tends to keep them pretty much which means that they can't generally propagate much above the stratosphere. And the waves that do get into the stratosphere tend to be quite strong, which means that they tend to saturate and break. And when they do, they transfer westward momentum to the mean flow. So keeping these two important facts in mind, this helps to comprehend better the phenomenon of polar vortex breakdown, also often accompanied by sudden stratospheric warming. What's going on for the case shown here, published in a review paper by Mark Baldwin, is in December of 2018, the study began with a quasi-stationary polar vortex in the northern hemisphere. Within a week, we have a wave number 2 pattern nosing into the stratosphere. The quantity plotted here, by the way, is vorticity. So think of it as kind of the second derivative of the of the pressure field. Within a week, we have a wave number 2 propagating up there, and which results in a sort of a stretched out, elongated vortex. The primary vortex over the pole, and then 2, one in North America, one in Asia. Within another week, the wave number 2, this guy has disappeared. And now we have pretty much only a wave number 1 vortex, known in meteorological parlance as a displaced vortex. And within another week, we see the influence of the equatorial propagation. The wave is kind of nosing further into the equator. And then eventually it just kind of breaks up and we're just left with the debris. And by the time it's broken up, that vortex that we talked about is completely gone because the planetary waves that have disturbed this whole pattern have dumped westward momentum into the mean flow, which is opposite to the direction that the initial vortex which is opposite to the wind direction of the initial vortex. So I didn't talk about this much, but the vortex basically gets set up by the equator to pole temperature gradient, which forces air from warm temperature and high pressure at the equator toward cold temperatures and low pressure at the pole. And then it gets deflected by the Coriolis force into this, come on, where's the pointer? Which gets then deflected into the west to east flow. And in order for that whole pattern to evaporate, to be eradicated, that means that the thermal structure has to change too. And so now we no longer have that cold pole anymore. And so that's where we get the definition of the sudden stratospheric warming, because accompanying the change from westward to eastward winds that creates this whole pattern here, we get the sharp rise in temperature. And by sharp, I mean sharp. This is a temperature change of about 50 degrees over the initial change is quite rapid. It's a change of 50 degrees sustained over a 2-week period or so. Anyway, so I've gone on a long time, but I wanted to present some appreciation for the dynamics of these waves. I'm going to close out the planetary wave discussion just with a brief mention of another category of planetary wave that is not quite so quasi-stationary. There are planetary waves that travel. The best known ones are the 2 in the 6-day wave, largely because they are found in the mesosphere and lower thermosphere, and as we'll see, in the thermosphere as well. And these waves are able to move past the surface and past the stratosphere because they are free oscillations that amplify in the kinds of wind conditions found in the mesosphere and lower thermosphere. So the two best known examples are the two-day wave, and this is actually a plot from UR's data showing that the two-day wave propagates up to about 120 kilometers. And then this is a more recent example. This is from the ICON MIGHTY data prepared for me by Joanne Wu. And this wave is also propagating up to at least 130 kilometers. So now that we know a bit about tides and planetary waves, let's talk about how they transmit tropospheric variability upward. As I pointed out, the diurnal tide in particular is forced by water vapor. And that has a lot of seasonal, intraseasonal, subseasonal, and interannual variability that can potentially be transmitted straight into the thermosphere by tides with deep vertical wavelengths. This is from a paper by Federico Gasparini, who analyzed diurnal tides, the convectively driven diurnal tide, DE3, in Sabre temperatures at 100 kilometers, showing the seasonal variability at 100 kilometers. And he also analyzed winds and densities from the Gochi mission, which represent the 260 kilometer altitude. And so the seasonal variability is being transmitted very, very faithfully up to at least 260 through direct vertical propagation. And this is a recent paper by Forbes, who really pulled off a remarkable feat with the ICON MIGHTY data and analyzed the propagation of the semidiurnal tide up to between 100 and 280 kilometers, showing that this particular semidiurnal convectively driven tide also gets up to about 280 kilometers. So I've shown the transmission of the effects of the surface water vapor and the convection upward. But and that dovetails very well with the Immel figure of that I showed early on. But what about that planet? What about those planetary wave perturbations at Hikomarka? What's up with that? So I want to talk a bit about how the stratospheric planetary wave variability and the sudden warming signatures might get beyond the stratosphere to imprint upon the thermosphere. So I commented that planetary waves do not propagate much above the stratosphere, generally speaking. And if you can't propagate upward yourself, then one other way to get upward is to get hitched to something that can. So planetary waves can start nosing into tide territory, into vertically propagating tide territory in the stratosphere. And they do get quite strong. So that sets up the possibility of nonlinear tide planetary wave interaction, which, if and when it happens, produces a whole spectrum of, tidal multiplicative responses, child waves, I kind of like to call them. The possibilities are mathematically infinite, but I focus on one that we were able to observe using data from one of the Navy's prototype high-altitude forecast assimilation systems that obligingly wrote out every hour, wrote their output out every hour up to 100 kilometers. And so we identified in the winter of 2009-2010, December 2009 to 2010, an evolving planetary wave at about 70 degrees over that 3-month period. This wave is being plotted at roughly 35 kilometers. And we identified one of those child waves that I predicted from tide planetary wave interaction, whose evolution really nicely tracks the planetary wave evolution. So observationally, these would appear, observationally, it certainly looks as if this child wave is coming from this parent wave. And in the same study, we did a numerical study where we actually confirmed that the source of this tide was the nonlinear interaction of this planetary wave with the migrating tide. So a couple of things to keep in mind. The planetary wave, these bursts of planetary wave activity that led to a couple of warmings during that season. These bursts, as I said, are confined to high latitudes and to the stratosphere. By interacting with the tide, their signature has reached the tropics, and it's even gone across to the opposite hemisphere. And another example of tide planetary wave interaction we saw in a recent paper by Guiping Liu, who analyzed, again, our favorite tide, the DE3, in both MLS temperatures at 80 kilometers and in cosmic F2 layer height, and found a 3.5-day modulation of the tide in both the lower thermosphere, in both the mesospheric data and in the F region data. And so this plot is really cool because it not only demonstrates a modulation of the tide by a 3.5-day wave, a wave known as a Kelvin wave, but this paper also demonstrates the ion-neutral coupling that the tides can affect, which is the topic of the next few slides I'm going to show. So having demonstrated how we can get variability directly into the thermosphere and how we can get planetary wave variability through the tide up to at least the lower thermosphere, now how does this all affect the ionosphere? How does this affect the plasma? So I've spoken about these modulated tidal waves, which are indicated here by the white arrows. So if you imagine that these are neutral winds at low geographic latitudes. So once we get into the ionosphere, you're dealing with a region where there's a lot of charged particles. And by the time we're at 100 kilometers or so, there is some potential for the charge to separate because the ions and the electrons have kind of different levels of collisionality and gyro rotation by about 100 kilometers. And so in the lower ionosphere, the so-called lower E region, which is around 110 kilometers, the ions are traveling with the neutral winds, but the electrons are not because they are instead rotating around magnetic field lines. So the neutral winds, which in this case can be planetary wave or seasonally modulated tidal winds. So the neutral winds are setting up an electric field, a so-called dynamo electric field, which is indicated here by this blue stripe. And at the magnetic equator, where the magnetic field lines are perpendicular, there is a efficient E cross B drift mechanism occurring through the Lorentz force on the particles at these altitudes on the electrons, and so that results in an upward drift of given the way that I've configured this particular plot. So that results in this upward drift, these green arrows. And at some point, up at about 600 kilometers or so, through diffusive forces, gravitational forces, plasma pressure gradient forces, the particles drift. The particles at the F region altitudes settle down. The magnetic. Okay, did we lose a slide here? We lost a slide, unfortunately. We lost the slide showing the particles settling down magnetic field lines, which I hate doing this, but try to visualize. In the original slide that's missing, there was some purple fluff going down these field lines. If you want to see it, go to NASA's conceptual animation lab. Oh, what a shame! That was my favorite slide. Okay, yeah, that was great. Anyway, so the smoking gun. It's too bad, because the smoking gun of the particles that are drifting down the field lines is this so-called equatorial ionization anomaly plot, showing all of the plasma variables not at the equator, but off the magnetic equator on either side of it. So we missed the fluff slide, but we have this slide, which I think is is one of the most spectacular I've ever seen, illustrating the equatorial ionization anomaly. It's from a paper by Gu et al., and it shows the neutral winds at 95 kilometers associated with a 6-day wave. And this is an impressively huge 6-day wave. I don't think I've ever seen anything like this before. The wave that Joanne analyzed had an amplitude of 15, and I did a 6-day wave study a long time ago, and the amplitude of the wave I looked at was more like 10. And so this is a rather huge 6-day wave, and it results in a very impressive total electron content perturbation that was about 15% of the background during a quiet time. So that's a pretty strong quiet time disturbance. So I'm going to skip over the second example of that and move to my last slide, which illustrates simply the changes to thermospheric composition that tides can induce. This is from a paper by Christopher Creer, a recent one, where he deduced diurnal tides in gold disk temperatures and ON2 ratio by forming a diurnal tide proxy through a dawn-dusk difference. So here's the latitude. These are gold longitudes. These are gold longitudes, latitudes. This is the Atlantic sector that gold observes. So there's the 12-hour difference, the diurnal proxy. This is the fit of these two convectively driven diurnal waves, showing up very nicely in both the temperature and the ON2 ratio. So I'm going to start wrapping up now, and I thought it would be kind of neat to see where we are compared to where we were the last time a CEDAR Prize lecture was given on this topic by Jeff Forbes in 2014. And Forbes, in his closing slides, left us with this list of challenges and outstanding questions. So let's see how far we have come. Forbes asked in 2014, to what extent do planetary waves penetrate above 100 kilometers? So we now know that the 6-day wave and that the 6-day wave and the 2-day wave propagate directly to about 130 kilometers, but that their influences are seen at least up to 400 kilometers. We saw the we saw the equatorial ionization anomaly in the 6-day wave, and I didn't present it, but but there have also been 16-day perturbations to the equatorial ionization anomaly that were published by Shangan. So the next question that Forbes asked was, so do the planetary waves modulate the tides, which then carry the planetary wave signatures into the ionosphere-thermosphere? Answer, yes. We saw in Guiping Lu's paper that the tides in the 3.5-day Kelvin wave were interacting and transmitting the 3.5-day tidal modulation into the up to the F2 layer. And although I didn't show this, Forbes has shown a lot of evidence recently for 2-day wave tide interactions in the plasma. How does the dynamo-driven wave spectrum above 130 differ from that below? Forbes asks. I would say that the jury is maybe still out on that one. Long waves clearly, are common to both regions, but otherwise we need better sampling of that region. Planetary wave, gravity wave interaction, a lot of progress there, but I did not make that the topic of this talk. Just a brief mention about the effects on the zonal mean wind. I didn't mention this in the talk, but Jens Oberheide showed that the sudden stratospheric warming induced changes to mean meridional circulations affect ON2 ratio. And finally, the question that both Forbes and I are leaving you all with is, how can we measure the ionosphere-thermosphere so as to enable us to really understand how the neutral wave variability drives the ionospheric variability? And my answer to that, which I hope future missions will be dealing with, is that we just simply need to measure neutrals and plasma globally, simultaneously, and over 24 hours at least, in order to really be able to sort everything out. So I'll leave you with that. I'm sure we'll hear much more about this as the week goes by. And thank you all very, very much for your patience. Thank you for putting it back up. Thanks, Rob. Sorry, I didn't think about that.
Winds and neutral depths.
Right. Thank you for that nice talk, Ruth. I have a question about the relationship between the sudden stratospheric warming and the planetary waves, which we always see in conjunction with the sudden stratospheric warming. And I'm naive about what comes first, the chicken or the egg.
The planetary waves. The planetary waves cause the warming. And in fact, when thinking about coupling of the stratosphere to the mesosphere, thermosphere, ionosphere, it's much more useful to think about the planetary waves because we don't always see you don't always see warmings. After all, strong planetary wave events. But so I would say that the thing to be focusing on is more the planetary waves and not necessarily the presence of a warming.
Ruth, we have a question on Slido from Li Ying. How often do planetary waves penetrate directly into the thermosphere?
I don't know, but there is somebody in the audience who does, and if she's willing to take the question, I'd be very happy to throw it to Lynn Harvey if she's willing, if she wants to get involved, if she wants to be put on the spot like this, because she would know more than me. Okay. But, or you can talk to people who know more, to me, or people who know more offline. Yeah.
You know, I take a kind of somewhat different perspective of the planetary waves and tend to look at them as 3D objects and vertical extensions of anticyclones up into the MLT region. And so I've got these visualizations that I can show anybody if they'd like to see of how the anticyclones move around the polar vortex, and they extend over a very deep layer. And at times, I do see these anticyclone structures extending across the mesopause. So,
can you put a number or a figure on how often that happens?
you know, it's difficult because I'm often basing these visualizations on, say, output from a whole atmosphere model where it's not exactly clear the accuracy of the winds up at those altitude levels. So we really, really need the measurements, like you said.
Yeah, I think we really just don't know. We don't really know enough about to answer that question.
Hi, Ruth. Thank you for a nice lecture indeed. Would you, I think it's well known that there is just a shear layer in the upper mesosphere at altitude of 110 to 120 kilometers. Has been demonstrated by the hundreds of TMA releases that Miguel Larsen has publicized. Could you comment on the relationship of the existence of this shear layer with the connection to planetary waves or tidal wave breaking? Is that
the short answer, John, is that I probably can't at this point, at least not at this particular minute, because it's not something I really have investigated, and I didn't really look into that as I prepared the talk. So it would be pure speculation, and I really can't. It's certainly well worth pursuing. So.
Thank you for a nice presentation.
Thank you.
I would like to ask, how can we measure the impact of greenhouse gases in non-migrating tides, for example?
How come or how do we measure the impact of greenhouse gases?
Yeah, how can we measure the impacts or isolate the impacts, the contribution of that?
Well, if you're referring to CO2, for example, so there are, I mean, one way that I can think of is to try to measure it kind of indirectly through the long-term variation of the tides. So, I mean, you would need a long data record. It would probably be easier to detect it at higher altitudes, which unfortunately is where we're lacking. Lacking the measurements. At higher altitudes, I mean like the lower thermosphere. So that's where we're lacking sufficient local time coverage to be able to sort out, tidal, tidal and mean temperature effects. But that's one way that I would try to go about it. Jens.
So, Ruth, I'm curious about your perspective about tidal sources in the thermosphere, and I'm not talking about the radiative absorption, but things like ion drag or gravity wave dissipation, in particular as a source of non-migrating tides. So what's your perspective in terms of relative importance compared to upward propagation and impacts on the IT system?
I don't have, I'm not a modeler, and so I don't really have those numbers. I mean, I think you would need to do some serious numerical modeling in order to determine, for example, how the effects of breaking gravity waves, the magnitude of the non-migrating tides forced by breaking gravity waves. So Sharon has specifically modeled this source, I think a number of years ago, a figure that I should have thought to check, to look into and put into this presentation, but I mean, it was substantial. It was quite significant, but I just can't really remember what that figure was relative to, for example, the forcing by the water vapor, by the tropical convection. But I can direct you to the paper or to Sharon.
I think the numbers were something like 5 to 15 meters per second at
The winds, you mean?
At 250 kilometers in that paper. Yeah. It was a Vadis et al. 2015, I think. Yeah. And what we did was we looked at gravity waves coming from deep convection worldwide over 13 days. And then we, when the gravity waves from deep convection dissipated from 100 to 200 kilometers, they deposited momentum and energy into the atmosphere. And then because they had the timestamp of the winds that filtered them from below, which was the tides and the planetary waves, when they dissipated, they re-excited tides and planetary waves at around 180 kilometers. And then I think your plot was either at 200 or 250 kilometers. And we saw a bunch of, I think they were 10 meter per second.
Yeah, it sounded
15 meter per second.
Yes, it's coming back to me now. There was a there was a composite DE3 wind study that I did, and the winds in the the winds at around 200 kilometers were probably on the order of 10 meters per second. But whether what I was seeing was the decay of the original wave or whether it was something your mechanism was starting up, I can't remember. However, that is a really, really clean way to assess, to isolate the effects of the gravity waves. And so it's sounding from the numbers that Sharon is saying that mechanism, the generation of tides in the thermosphere by dissipating thermospheric gravity waves, it sounds like it is on the order of what the winds were associated with the decaying of the tropospherically forced wave at those altitudes. So a significant source.
Great presentation.
Thank you.
One thing I probably didn't have time to cover was the lunar tide. And I was wondering, does the lunar tide also interact with planetary waves?
I don't know. It has not, well, okay. So there are two ways to think about it. I don't know if they interact with planetary waves in the way that I specifically showed here, because that hasn't been measured. But during sudden warmings, the change to the background temperature is thought to alter the vertical propagation characteristics of the lunar tide. And so there have been studies showing that the lunar tide is sensitive to sudden warming, and that the lunar tide amplifies during sudden warming. I did do some lunar tide stuff, but I skipped that slide because we were running late. But anyway, so that is certain. It's worth looking at, and the gold study I did on the lunar tide was initially motivated by hoping to see changes to the lunar tide in the gold data during a sudden warming episode, and as it happened, I didn't see anything. So, yeah.
Okay, so I have another question about this sort of SSW things. So I was reading around a little bit about this, and you can tell me if this is too specific. The primary cause of the polar vortex breakup, some people say, it's planetary waves 100%. Some people say, I'm not really sure about this, And I was reading around, and it was really hard for me to know what the confidence is, you know what I mean? So you having, knowing more about this than me, is that 100% like how it is, or is that what we think right now,
I'm not sure I can answer. I can tell you if it's 100%.
Yeah.
If it's a 100% thing. I'm not a big expert on the stratospheric planetary wave sudden warming stuff. I just kind of gave the kind of the historical overview. So. Thanks.
I have a loud voice. A comment and a question. The comment, I think you and I agree that a big uncertainty is also, which is a subtext of all these questions. We don't understand the day-to-day variability of winds and other aspects of the meteorology in the lower thermosphere. And so these observations that will come up in the next 10 years, we need also continuity of observations over a long period of time. And I know you and I agree, it's just a comment. The question is, how well do we understand the physics of the lower thermosphere? So you described very well the interactions of wind and dynamo coupling. Do we understand all the physics? Is something that you think that we are missing? Because most models are not doing very well in representing that area.
I think that the ICON mission, among other things, has demonstrated that certainly the thermospheric, that certainly the F region is controlled by more than E cross B drift. The ICON mission was able to actually do one-on-one matching between neutral winds and the plasma drifts along identical coincident magnetic field lines. And they showed, I think, about at most a 60%, a 0.6 correlation between the neutral winds and between the observed winds and the dynamo-driven neutral winds. So I think there's a lot more going on that needs to be understood.
And this is also a specific question. You presented the results of the interaction between the planetary waves and tides. So I also did a case study of that, and what I saw is really the planetary wave first modulates with the tides, and then at the beginning, and then later on it starts interaction, and we could be able to identify the child waves. Like, do you also see this as well? Is there any comment or suggestion of like telling if the modulation comes the first and then the interaction coming later on, or they could actually happen at the same time?
I have not looked at this closely. I have not looked at the evolution of it very closely enough to be able to tell you that, because I was working mostly with currently have. And I mean, I'm biased. I'm thinking, for example, of ICON. It's very difficult to know whether we're seeing tides, planetary waves, planetary wave period modulation of tides in the F region. So it's hard to unpack that.
Okay. The next question, is there an impact of climate change in the lower atmosphere causing polar vortex breakup variations?
Probably yes, but it's not my area, and so I don't really want to. It's not a great question for me to have to answer, but I would say yes. Models have shown impacts on polar vortex evolution and breakup relating to climate change.
Okay, and then the last one is, what would the perfect experiment to characterize the physics and chemistry of the planetary wave disturbances above the mesosphere? Measurements, space, ground. If you could have anything you want.
Well, if I could design my ideal experiment, and this is irrespective of, the actual, what the actual physics may be and what the measurement techniques would be. But if I could design the perfect experiment, I would probably take the one of the main principles of the mission, which was the conjunction, which was the conjunction of neutral winds and plasma drifts along common magnetic field lines, and try to have that be a permanent measurement feature, and measure the region in between the lower thermosphere and the topside ionosphere dedicatedly 24 hours globally. That's what I would do. Yeah, for all time. Yeah.
Thank you so much, Ruth, for this very stimulating, very interesting discussion in the community. So one topic that we have not touched today, I was very interested in your view and your comments about interhemispheric coupling between winter stratosphere and summer mesosphere. Mechanism, how well do we understand this mechanism, and how large is the strength of this coupling? Where are we as a community in understanding these effects?
Well, I haven't seen a whole lot about it in recent years. The three approaches to this that I've seen are there has been a lot of numerical modeling on the role of gravity waves in interhemispheric coupling, and there's a great deal of numerical evidence for that, and observational evidence is kind of harder to come by, and it generally is in the form of evolution of polar mesospheric clouds, and whether that evolution dovetails with the predictions of the gravity wave driven mechanisms. Then there was a different mechanism completely involving inertial instability that we were able to observe. And I wrote a paper about that a couple of years ago. And it was successful in that the the observations and the observation-driven modeling dovetailed well with the evolution of the polar mesospheric clouds. But that was only one study, and if there was the bandwidth and the money, it could probably it could be possible to attack that and try to delve into it statistically. Haven't had the opportunity. And then while I was in the throes of the inertial instability study, Ann Smith published a paper showing that statistically there was a connection between the northern hemisphere wintertime planetary waves and the cold summer mesopause, and the warming of the cold summer mesopause. She showed a connection, a statistical connection that had absolutely that did not require any kind of intricate gravity wave dynamics or inertial instability dynamics. She proposed that it was just simply a result of the planetary wave-driven mean meridional circulation, a paradigm developed 40 years ago. She argued that it was just an extension of that simple mechanism to higher altitudes that had never really been dealt with until now because, data had not been available or it wasn't on anybody's mind or whatever. So the options run from the simple, and the tradition and the old stuff to the extremely intricate and the recent. And I haven't seen a whole lot in the last couple of years or so. So
this looks like we have a lot of room to study it with modeling and observations.
yeah.
Any more questions in the room? Otherwise, we'll take that as last one. Yeah. Okay. There's one more on Slido. Has the southern hemisphere polar vortex and breakdown being observed at the same time as the northern hemisphere?
Yes, I mean there have been southern hemisphere warmings. They are apparently not as frequent because the ocean, land, the ocean continent surface characteristics are not as dramatic. And they're not going to occur at the same time because they're winter phenomena. So the southern hemisphere winter is going to be the northern hemisphere summer and vice versa. So they will not be simultaneous. Have I said something wrong? Did I totally misinterpret?
Yeah, Ruth, you probably misunderstood the question.
I guess so.
The southern hemisphere polar vortex and the northern hemisphere polar vortex cannot form at the same
That's
time.
what I said. They can't. They can't occur at the same time.
Yeah, so I don't think they can break up at the same time.
Okay, I think that's all. Thanks. Thank you very much, Ruth,
Thank
for
you.
your all talk.
Thank you, please.
I'm sorry I went over. I'm sorry I went over time.
No, you're doing great. We
Oh,
have
I'm
plenty of
supposed to-
time.
Am I supposed to-
Okay, let me thank Ruth on behalf of entire community once again for wonderful lecture and all this wonderful discussion. You see how many questions it stimulated. And one aspect I wanted to mention, you noticed how in this prize lecture, Ruth did not really talk about her own work as much about community effort. In truly CEDAR spirit, Ruth highlighted our achievements and our challenges as a community, and I really appreciate this. And to memorize this day and this recognition, let me thank you. Let me give you.